enjoyed talking about it with you yesterday. I think we're going to have fun today. Okay, Chemistry 3101. We left off at section 15.10. Okay, and I just want to do a quick review of this section with you. Section 15.10, which deals with nothing more than how we analyze a proton NMR spectrum. And we're going to look at some spectra today to get used to solving structures, looking at proton NMR spectra. But there's kind of a step-by-step process that we take. First step is that we calculate the HDI. So you're going to need to know the formula for HDI. And we looked at that way back in chapter 14, that HDI is equal to 1/2 of 2 times the number of carbons plus 2 plus the number of nitrogens, subtract the number of hydrogens, and subtract the number of halogens. And remember, if you have an HDI of 1, that would mean that you either have a pi bond or a ring, and so on and so forth. After that, we take a look at the number of signals and the integration, because the number of signals tells us the number of unique types of protons we have in our molecule. And integration, of course, tells us about the number of protons that are represented by each signal. Next, we analyze the signal and we draw fragments. So when it says analyze the signal, that's where we look at the multiplicity and we apply the n+1 rule. So we're going to review the n+1 rule today. So make sure you're fully aware of that. Remember, we looked at an ethyl group and an isopropyl and a tert-butyl, and we saw that they had very characteristic multiplicities that we can use to identify those groups. So we're going to get some more practice on that today. Then you take those fragments. You think you have an ethyl, you think you have a methyl or a tert-butyl, and you put them together into some kind of structure. And what's nice about solving spectra problems is that at the end, you can verify to see whether your structure is actually consistent with the spectral data. And again, that's the kind of 5-step process that is laid out for us in our textbook, and it works very well when we're trying to elucidate the structure of an organic molecule using proton NMR spectra. Well, if you go all the way back to the beginning of this chapter, what I said was you can run proton NMR spectra on you can run an NMR spectrum on any kind of nucleus that possesses nuclear spin. But in this class, we're concentrating on protons, and we're also going to take a look at carbon-13. So carbon-13. Now, we know that protium, or hydrogen-1, is the most abundant isotope of hydrogen by far. The others are deuterium and tritium. And since protons, or protium, or hydrogen-1 is the most abundant isotope of hydrogen, the proton NMR signals are generally speaking going to be very strong. But we know that the most abundant isotope of carbon is not carbon-13. It is in fact carbon-12. So carbon-12 makes up about 98.9% of all carbons, and carbon-13 only makes up about 1%. And so if you run a carbon-13 spectrum on a molecule, there's only about a 1% chance that your carbon actually possesses nuclear spin. Therefore, you need to have a much more concentrated sample, or you've got to have a much more sensitive receiver coil in order to get a good carbon-13 NMR spectrum. Well, something that I think students usually like about carbon NMR spectra is that when we were dealing with proton NMR spectra, we had to consider the chemical shift in parts per million, and we had to also consider splitting, meaning the multiplicity, the n+1 rule, and integration. However, in carbon-13, the only thing that we need to worry about is the shift. There is no splitting in carbon-13 spectra, and there is no integration. So again, only the number of signals is what we're interested in. Only the number of signals and the chemical shift are going to be considered. We don't worry about splitting, and we don't worry about integration. So it's actually a little bit simpler for many students to look at a carbon-13 spectrum. In carbon-13, if you're wondering, well, shouldn't you get coupling between a carbon-13 nucleus and a proton? If a carbon-13 nucleus is attached to a proton, then there should be splitting. And the answer is, yeah, there is. However, since protons are abundant, the splitting is often so complex that the spectrum becomes just very difficult to decipher what's going on. It's practically unreadable, and that's not useful for us at all. And so 99% of the time, the carbon-13 spectra that we're going to look at are going to be what are called carbon-13 decoupled spectra. So we call it a decoupled spectrum. And what that means is that we set up the experiment in such a way that we excite all the hydrogen nuclei simultaneously with the carbon-13 nuclei. And basically, it just prevents the splitting from occurring. So we just end up seeing nothing more than a bunch of singlets. We don't see any triplets, doublets, quartets, or anything like that. We just see singlets in a carbon-13 NMR spectrum. Now, if you're wondering about the chemical shifts of the carbon atoms in a carbon-13 spectrum, we remember that in proton NMR spectra, for protons, the chemical shifts were in the range of 0 to 12 parts per million. However, in a carbon-13 NMR spectrum, we have a much broader range of chemical shifts. They actually go from 0 to 220 parts per million. And so, so we have a much broader spectrum, and each signal in that carbon-13 is going to represent a unique type of carbon. So the number of signals that we have tells us about the number of unique types of carbons. Now notice that I didn't say each signal represents a carbon. I said each signal represents a unique kind of carbon. And why did I say that? It's because planes of symmetry, axes of symmetry can cause carbon atoms to be chemically equivalent or electronically equivalent, much the way we saw with protons at the beginning of chapter 15. Take, for example, these three compounds here. This one is called orthoxylene, this one is called metaxylene, and this one is called paraxylene. The names aren't important, but if you look at these compounds carefully, you can see that in this compound here, I have 4 unique signals because I have a plane of symmetry running through the molecule right here. I have that plane of symmetry. And so you can see that this carbon and this carbon are chemically and electronically equivalent. These 2 carbons are equivalent. These 2 carbons are equivalent. And these 2 carbons are equivalent via the symmetry. Therefore, we see a total of 4 signals. In the next compound, we see that we have 5 unique signals. And I'll just go over a little quicker now. You can see the 2 methyls are equivalent. We have this carbon and this carbon as being unique. And then we have this carbon as being unique. And then lastly, we have this carbon as being unique. So we have 5 unique symbols. I can fill in these ones here and this one here. So 5 unique symbols for that one. Whereas in the last one, we have 2 axes of symmetry. And so we only have a total of 3 signals. Give me a thumbs up if you follow me on the number of signals in the carbon-13 NMR spectrum for these compounds. Just by visualizing the planes of symmetry, right? So we talked about these 3 compounds or compounds similar to them, I can't remember exactly, yesterday. We said we could run a proton NMR on these compounds and we could distinguish between them very quickly. You can see that you could do the exact same thing with a carbon-13 NMR spectrum. It is a very powerful spectroscopic method. We can get a lot of information very, very quickly. So carbon-13, very important. Now, if you're wondering about the chemical shifts, the different types of carbons, this is a summary of some of the chemical shifts that are provided in our textbook. This isn't an exhaustive list of what's in the textbook, but this is essentially a little bit expanded version of the table that I will give you for your quiz. If you looked at, and I know you all have, the table of IR and NMR shifts, these are the ones that we provide for you. We don't give you these little structures here, but we basically just tell you, you know, this is where you're going to see your chemical shifts. So this is kind of like a version of figure 15.22. So we could put here, I'll put here C figure 15.22. Let's take a look. If you have a carbon that is sp3 hybridized, it's going to have a chemical shift of somewhere between 0 and 50 parts per million. If you have a carbon that is sp hybridized, or if it's attached to an electronegative element like nitrogen and oxygen, it's going to have a chemical shift between 150 parts per million. All of our sp2 hybridized carbons, whether they're in an aromatic ring or if they're part of a double bond, those are going to be between 150 and 100. And all of our carbonyls, so whether they're in an amide or an ester or a carboxylic acid or an aldehyde or what have you, those will be in the range of 150 to 220 parts per million. Now, again, you don't have to memorize this table necessarily for the quiz because I will give you the handout. However, I highly recommend that you try to familiarize yourself with this the best you possibly can because it's annoying to keep going back to the table over and over and over. And also, there's much less chemical shifts to remember for carbon than there are for proton. Now, if you want a more exhaustive list of chemical shifts, you could see table 15.4. And that table goes into a little bit more detail about the chemical shifts for methyls, methylenes, methynes, carbons that are attached to the halogens like iodine, bromine, chlorine, etc. So it goes into a tiny bit more detail, not a ton more detail, but a little bit more detail if you want to get that. So we'll put here C table 15.4 for more detail. All right, there we go. All right, and this brings us to our last section for us in this chapter, which deals with what's called depth carbon-13 NMR spectroscopy. And what I told you is that carbon-13 NMR spectra just give you a bunch of singlets. And those singlets don't provide any information about the number of hydrogens attached to each carbon, unlike we saw with proton NMR spectra, where we could apply the N+1 rule. We can't use the N+1 rule with carbon-13. And so we have a workaround for that, which is an experiment called the depth experiment, or a distortionless enhancement by polarization transfer. You don't need to remember what it stands for. Just as long as you know the acronym is good enough for me. But what's cool about depth is that we have two types of depth experiments, and I'm not going to go into the details of those. Even our textbook doesn't really go into the details. But using these two different experiments, which have a different pulse sequence than a normal proton decoupled carbon-13 spectrum, we can identify a carbon as either being a methyl, a methylene, a methine, or a quaternary carbon. The reason why we can do that is because if you run a decoupled spectrum, you see all of these carbons show up in the spectrum. Everything comes up in the spectrum. Whereas if you run the depth 90, the only thing that you see are the methines. And so you're able to identify the methines, right? When you run the depth 90, you're able to go back to your decoupled spectrum and you can tell exactly which peaks are methines. Then if you run a depth 135, what it does is it gives all the methyls and methylenes, the methyls and methines will have positive signals. And so that way you're able to distinguish the methyls from the methines, and anything that's a methylene is going to have a negative signal. And so you're able to identify it. Now you've identified the methyls, the methylenes, and the methines, and anything that's left over is a quaternary carbon. And just like that, we're able to distinguish between all four types of carbons by running 3 experiments. Again, the first one is just the regular decoupled spectrum. Then we do the depth 90, then we do the depth 135, and we are able to identify every type of carbon in our carbon-13 spectrum. If you're wondering, do you have a summary of that, Mr. Dion? Yes, I do right here. So again, in our decoupled spectrum, we see all the peaks as singlets. In the depth 90, the only thing that shows up are the methines. Then when we run the depth 135, we're able to determine which carbons are the methyls and which ones are the methylenes. Anything that's left out is one of the quaternary carbons. So just like that, we're able to identify all of the carbons very quickly. So what I want to do is show you a little example of this. So just give me a second here. right here. So let's take a look at a problem where we have to apply this table. So we're going to have to refer back to this because I wouldn't expect you to have this memorized right away. That would say that it would be impossible. But in the new version of our textbook, this is actually table 15.5. In my slide, it says table 15.4, but anyhow. There we go. So let's go up and let's take a look at a practice problem that involves carbon NMR spectra. It says, determine the structure, and I'm just reading right here, determine the structure of an alcohol that has a molecular formula of C4H10O that exhibits the following carbon-13 NMR spectra. First thing we notice is that we have the molecular formula. I did a little math while I was reading the problem, and the HDI for this compound is 0. So there's no rings and there's no double bonds in this compound. Well, now let's take a look at the broadband decoupled. We have 1, 2, 3 types of carbons. Now notice we have a total of 4 carbons in the molecule. That means that there must be some symmetry somewhere in the molecule because we're only seeing 3 signals. Now we look at the depth 90. Again, by looking at the decoupled, we don't know whether these signals are methyls, methylenes, methynes. But if we go to the depth 90, we see that we only have 1 signal sticking up. And remember that the depth 90 represented a methine. So we know that this signal here must represent a methine. Okay. Next, if we go down to the depth 135, we see that we have 1 negative signal, 1 signal pointing down. That's a methylene. And anything else that's pointing up that we didn't identify before must be a methyl. So that means that, did I label that as a methylene when I meant to make it a methine? Oops, my mistake. So this isn't a methylene, it's a methine. There we go, that's a little bit better. This is our methylene, sorry, my mistake. And then this must be a methyl group. Okay, again, all I did was I looked at the depth 90 and the depth 135. I used this table and I was able to identify every carbon in the spectrum as either being a methylene because it's pointing down here, a methine because it's the only one that shows up in the depth 90. And so what's left over must be a methyl group because it shows up in the depth 135. There we go. Now, again, you see that we have 4 carbons in our compound, but we only have 3 carbons here. And since it's an alcohol, we also have a hydroxyl. If you tally up the total number of hydrogens that we have right now, we have 1, 2, 3, 4, 5, 6, 7. Well, in order for there to be another carbon, because we're missing a carbon, and 3 more hydrogens because we're missing 3 carbons, what that means is that this must be 2 methyl groups, right? It's the only possible way that that could exist, that we could have this formula would be to have 2 methyl groups, 1 methylene and 1 methine. Give me a thumbs up if you're with me so far. Is everybody with me on the rationale to this point? Great. Remember, if you have any questions, don't hesitate to interrupt me and just say, hey, I don't get this, that's no problem. Okay, so now we have to, if you like puzzles, you're going to like organic chemistry, right? We have all of these pieces. We have a hydroxyl, we have a methylene, we have a methine, and we have 2 methyl groups. Now what we're going to do is we're going to try to put them together. Well, the only way that we could put these together is if the methylene has 2 bonds, and if the methine has 2 bonds. Let's see what we could do here. I didn't give myself a lot of room to solve this, did I? What if I try something like, if I take the methylene and I attach it to the methine, like this, and then if I put a hydroxyl here, and if I put a methyl group here, and then if I put a methyl group here. Could this be a possible structure for the molecule? Could anybody tell me if this looks reasonable or not? It fits the formula, and there's nothing wrong with the structure, but does it fit the spectra? If you're not sure, what you want to do is you want to look at these two methyl groups here. Okay, so what I've drawn is this. So what we have is this. All right, and you can see that the two methyl groups that I have in the red circles, those are not chemically equivalent. They are not electronically equivalent. They are actually different from each other. So that means that this structure cannot be correct. Okay, that structure cannot be correct. Is there another way that I could connect those atoms together? Okay, since this is incorrect. The answer is yes, there is another way I could connect them. Now, again, I'm kind of running out of space here. Let me just move this out of the way a little bit here. Okay, there is another way that I could connect them. What if I had them connected like this? If I had the two methyl groups both attached to the methine like this, then I had the methylene, and then I have the hydroxyl. My question to you is now, are these two methyl groups chemically and electronically equivalent? Would they be equivalent? Yes or no? Could anybody answer that? I would say they are, because we have a plane of symmetry running through the molecule like this. Okay, we have a plane of symmetry here, and so those two methyl groups are chemically equivalent. Therefore, this must be the correct structure. So this is correct. Oops, correct. Now what we want to do is we want to annotate the spectrum. So we want to identify all of the carbons in here. Notice, when we're annotating a spectrum, we always start on the right-hand side and we go towards the left-hand side. And every signal we label with a letter of the alphabet, always starting with A. So we have A, B, and C. Now we go over to our structure. We write A next to, I'll use a different color. Let me rewrite the structure. I deleted everything by accident. Let's rewrite it. Can I do this? No. All right. Anyhow, so here we go. We have A, we have B, we have C. So these would be my A carbons here. This would be my C carbon, and this would be my, this would be my B carbon. And that is our structure. Give me a thumbs up. Is everybody with me on that? I just want to make sure we're all on the same page before we move on to another problem. Okay, cool. Sorry that I deleted everything, but anyhow, hopefully you got the crux of that one. All right, and again, don't hesitate to interrupt me if you're unsure of a question. Let's take a look at another one. And again, this is another one you can see comes straight out of our textbook. It's just question 15.28. I just copied and pasted in here. So we have a broadband decoupled spectrum. What does it say? It says, determine the structure of a compound with the molecular formula C5H12O that exhibits the following broadband decoupled and depth 135 NMR spectra, carbon 13 NMR spectra. The depth 90 has no signals. So if we go back here, if the depth 90 has no signals, okay, that means you have no methynes. So there are no, we'll put here, no CHs. All right, so let's take a look. If we look at the broadband decoupled, we have A, B, C, D, and E. We have 5 types of carbons in our molecule. What are the types of carbons? Well, there's no methynes. Everything that's pointing down is a methylene. So that means that this is a CH2. This is a CH2. These are both pointing up. So these must be methyl groups, CH3, CH3. And then this signal up here doesn't show up in the broadband decoupled, and therefore it is a quaternary carbon, right? So it must be attached to, something like this, okay? However, if it has a chemical shift above 200, what does that tell us? Okay? If it has a chemical shift that's above 200, that means it's got no protons. It must be a carbonyl. Right? If you go back to the table that we looked at, anything above 200 is definitely going to be a carbonyl. So that means that we have a ketone, and that's good because if this is our molecular formula, we have an HDI that's equal to 1. And there it is. It's in our double bond. So now we have all of the pieces. We have a carbonyl. We have two CH3s that are not equivalent, and we have two CH2s that are not equivalent. Again, look, we have 1, 2, 3, 4, 5 carbons, C5. We have 3, 6, 8, 10 hydrogens. We have 1 oxygen, and we have our double bond. Are you with me up to this point? Just getting this far. Everybody with me up to there? Okay, and again, never hesitate to interrupt me. Okay, so how are we going to put this together? I'm going to write down one structure, and I want you to tell me if it's reasonable or not. One way that I could put all these atoms together would be something like this. Make a ketone like this. If I write out this ketone, would this be consistent with this, with these spectra? Clinton, you're 100% right. Could you tell us why, Clinton? And you don't have to unmute your mic if you don't want to. I could just read what you type. And if you want to unmute it, that's cool too.
There's an axis of symmetry.
Darn right. Yep, perfect. Okay, maybe I'm going too slow. I don't know. But anyhow, there's an axis of symmetry, isn't there, Clinton? So that means that these two methyls would be chemically equivalent. So you wouldn't see two different signals. They would overlap. They would make just one signal, like in the previous problem. And Clinton is also saying that these two methylenes are identical. So then the methylenes would overlap. So this makes no sense. This cannot be right. So we can put a big over that. That doesn't work. It's kind of tough for me to ask you if you have any other ideas, but I think that hopefully you're following me, that the best way to put all these together would be to have one methyl on one side and then to have the two methylenes and then, the two methylenes like that, and then have the methyl group over here like this. Now we have something that's completely different, okay? We have two methyl groups that are not identical. We have two methylenes that are not identical, and now we can annotate our spectrum. So my question to you is this. I'm going to highlight this methyl in green, and I'm going to highlight this methyl in yellow. The methyl that I have highlighted in green, would that be signal A or C? The one that's in green, would this be A or C? Could anybody answer that? Keep in mind that C is the most de-shielded. Right? If you look at A and C, we see that C, you see that C is more de-shielded than A. That means it's closer to something that's withdrawing electron density, right? Like the carbonyl, which is an electron withdrawing group. And so this carbon, the one that I have highlighted in green, would be C. The one that I have highlighted in yellow would be A. The one up here, this must be the carbonyl, carbon, E. And then between D and B, again, D is the most de-shielded, so that's the one that's going to be closest to the carbonyl. So this would be D, and this would be B. And there you go. So that's a little bit of information about carbon-13. So that's kind of an introduction to it. And I'll just tell you a couple of other, short things, is that we don't always run every single experiment. We don't always run a decoupled, then a 90, then a depth 135. Sometimes we'll just run the broadband decoupled. The bottom line is that what I need to do as your instructor is to provide you with enough information to solve the problem. So if I ever give you a problem, you'll always be provided with enough information to solve it. Okay, I'll never leave you hanging so that you are guessing how to solve a problem or anything like that. So there you go. That covers the whole section, the whole chapter 15 on NMR. If you go back to the slides, you'll see there's one short slide about MRI, I'll leave that as an FYI thing. I won't be quizzing you on that whatsoever.